Hi. Okay, getting into some more good stuff, all right? We're going to incorporate buffers into our acid-base equilibrium. So it's weak acids and bases, buffers, equilibrium, all right? So get the practice problems attached. They're down below. I kind of left some room for notes. So sorry if I didn't leave enough. And turn on your brain, calculator, probably periodic table. Nah, probably not. And oh, I gotta share my screen. Share screen. Now I could share my screen here. What was I just doing? Okay. Oh, I've been sitting all day. Okay, so the first thing we want to talk about is the main idea here is something called buffers. All right, that's something called buffers. I wish I could change the color of the background. At night, it turns black. Buffers. Actually, that might be my only other app. What is a buffer? Okay, think about in environmental science, a buffer would be like a region that could protect something, right? So maybe you got the ocean, and then in Florida you have a bunch of marshes, and then you have the land. That marsh is kind of like a buffer. It can absorb that water so this doesn't get to the land. In chemistry, a buffer is a solution that resists a change in pH upon addition of an acid or a base. Okay, and for us, the acid will be hydrogen and the base will be hydroxide. All right, so it protects the fact that the solution is a buffer. The pH of the solution is protected. A buffer contains a weak acid and the conjugate base in the form of a salt. Remember, a salt is simply an ionic compound. It could be vice versa, right? But you're usually going to see it this way, but it could be vice versa. Okay, or vice versa. So it's got to be weak. So that could be like HF and the salt NaF. A salt, and that would be a soluble salt. That's why I put it with sodium. Okay, we don't want to start getting that confusing. So what we have here is a system that contains this, and this as its major species. If I was to add an acid to this system, is there anything here that it would react with and that would form? And the answer there is yes. This would form HF, which is a weak acid, and therefore will form. Okay? So the conjugate base of my weak acid, which came from my soluble salt, is helping to protect my pH when a hydrogen acid is added. Instead of the hydrogen going into the solution and decreasing the pH, it is forming HF. What if I was to add a base to this? Is there anything here it would react with? And the answer is yes, it would react with this. And what would happen is that hydroxide, hold on, I was going to write a little note out here. Hydroxide, guys, is the strongest base there is. Okay, so hydroxide is going to want to take his hydrogen back and form water. Let me write the equation for this, right? If I had HF, my equation would be F plus H yields HF, right? I'm sorry, I apologize for that. But if I was to add an acid to that solution right here, we would see that what would happen with the hydrogen would react with the fluorine. So that's what we have referenced over here. If we were to add a base, what you need to learn to recognize is oops, don't do that. Is that this base will react with the weak acid, okay? So our equation, we are adding the base, so it must be a reactant. It will react with our weak acid and produce an equilibrium situation that will give us HOH or H2O and the fluoride ion. So this is a KB. That's also a KB, isn't it? That's weird. I don't want to talk about that right now. Okay. Actually, it's Ka. Okay. So what we see is this solution that contained the weak acid and a salt that contained his conjugate base has the ability to absorb hydroxide, thus allowing it to not become a part of the solution, and it will not cause much increase in pH, just a slight, okay? And when we added the hydrogen, the conjugate base of the weak acid absorbed it. It did not go into the solution, so there's no H plus, right, to decrease pH. And you just have to understand that. Okay, now the pH will change ever so slightly, and this buffer can only last for so long. It has a capacity. All right, let's go ahead and get to work. Okay, this might be, this is another one of those ones, all right, kind of like last time, but these are the only questions here. We've got 0.100 molar ethanoic acid. That's our acetic acid. It's not H2, guys. It's HC2. HC2H3O2. Ka equals 1.80 times 10 to the negative fifth. It is mixed with a 0.100 molar solution of potassium acetate. All right, recall that this completely dissociates into potassium ions, acetate ions. All right, potassium will always be spectator ions. We've also got this. So these are our major species and water, right? I'm going to always write water. Water is here as well. So these are our major species present. Let's look at what we're asked for. Calculate the pH of the resulting solution. All right. Okay. So, and what is my reaction going to be? I've got to figure out my reaction. Oh, there is no reaction. I just have a solution. So let's go like this. Since we have a Ka for acetic acid, let's write that expression. I'm sorry. What are we looking for? pH. Okay, this is all we need to do here. I didn't need my major species. I didn't have a reaction, right? I didn't have a reaction. I'm just sitting here, right? I'm just sitting here. I apologize. So initially, making this too hard. This is 0.100. And what we have is a common ion. We also have 0.1, right? 0.100 molar acetate ion because, right, it's a potassium and acetate. So the concentration of the compound is the concentration of the ion. So this is also 0.100. Now we do not initially have any of this. So essentially, people, buffer equilibrium problems are just like common ion problems in terms of solving. Now, the change will be minus x plus x plus x, and at the equilibrium, it would be 0.100 minus x, 0.100 plus x, Ka equals 1.80 times 10 to the negative 5 equals x times 0.100, the plus x term, and the minus x term is negligible. It will be over 0.100. This cancels. X equals H plus equals 1.80 times 10 to the negative 5th. The pH is equal to the negative log of H plus is equal to the negative log of 1.80 times 10 to the negative 5th. And that should be less than 5. In fact, its pH equals 4.74. Right, so that is the pH of the solution by itself. I have a buffer solution with a pH of 4.74. I've got equal ratios of weak acid and conjugate base. That is an ideal situation. That's an ideal situation. It allows for both acids and bases to be absorbed without the pH changing much. Let's go ahead and look at number 2. All right. Number 2 says the question for number 2, it says why? Why is the 1-to-1 ratio optimal? So the 1-to-1 ratio allows for pH to equal pKa plus log B over A. All right, we're going to get into this later. When ratio, right? When ratio is 1-to-1, then the log of 1 equals 0 and pH equals pKa. This is an optimal buffer. It allows for both acids to be added and bases to be added, and with a very slight increase in pH, and it buffers for the longest time in both ways. All right, so that's the answer to 2. Number 3 says pKa equals 7.6. 1/3 protonated weak acid. How's that written? Let me read it. Certain biological molecule has amino group. An amino group is an NH3 on its side chain with a pKa of 7.6. Calculate the pH that will result in 1/3 of its amino groups being protonated. You really don't need to worry about this, but let's see. Let's call that NH3 plus, and then we would have the NH, 2. This would be the 1/3 is protonated. You guys will not have problems like this, I don't imagine. And then this, but it builds, and this is 2/3 protonated. So this is 0.33, and this is 0.67. According to that equation we just wrote up there, pH equals pKa plus log B over A. This is actually the Henderson-Hasselbalch equation. It will show up later. I wish that we weren't seeing it right now, but you'll see why we are. It's actually a later topic, but there's no reason it should be brought up now. Okay? This is my acid. This is my base. pH equals pKa plus log the base over the acid. pH equals pKa 7.6 plus log 0.67 over 0.33. Put it in your calculator. Put it in your calculator. Stop and put it in your calculator. 7.9. So they just wanted you to understand how to do that. Okay. Using that Henderson-Hasselbalch equation. We'll see that pop up again. You rarely see questions the way that one just came at you. The next question, guys, gives you a pKa of at 4.75. It's of ethanoic acid. We can just call that HA if we want. Or we could write HC2H3O2. All right, maybe we'll do that. Okay. We need to know the pH of the solution, right? And we've got 40.0 milliliters of a we look like we have a lot of work to do, molar hydroxide. And we've got, what else do we have here? Is added to 50.0 milliliters of a 0.75 molar, and that looks like that would be our acetic acid. Okay. Okay. So this is the first time we've had a problem like this, okay? I've got hydroxide. I've got acetic acid. And I am adding the hydroxide to the acetic acid. So there are two steps to this problem. There is the stoichiometry step. And then because I have a weak acid over here, I have my equilibrium step. So the reaction has to go to completion, and then equilibrium has to be reestablished. Okay? Now, what I have here is, I'm going to change my color up. Let's go to blue. What I have, oh dear goodness gracious. What we have here, last time, is we are taking our solution of acetic acid. We need to do some, we've got a stoichiometry part first, so we've got some work to do. We need to get the moles, right? Slow down, Miss Murphy. So because we have a stoichiometry step, we must have moles. All right, so let's look here. This is 40.0 milliliters. Every 1,000 milliliters is 1 liter. Every 1 liter is 0.040 moles. So we have 0.00160 moles of what? Moles of hydroxide. Okay. Over here, we've got our 50.0 milliliters, 1,000 milliliters, 1 liter. Every 1 liter is 0.75 moles. So that's going to equal 0.00375 moles of our acid. Okay, in this reaction, we have the acid, and we are adding the base, and we will get what? We will get water, and the acetate ion. Okay? Okay, cool. Now, those are moles. Let's go ahead and get our actually, you really don't have to do that. I'll do it later. I'll do it later. We learned some things. Okay, so let's start with our initial, do our change, do our equilibrium. That gets a negative. And let's do our stoichiometry part. So let's plug in our moles. That's right, we need moles for the stoichiometry part. OH, well, let's see. This first substance is 0.00375. OH is 0.00160. OH is the strongest base there is, right? He's acting like a base here. He will take every bit of hydrogen he can. So he will be the limiting reactant. This is 0, this is 0. Remember, water doesn't matter anyway. So it's minus 0.00160 minus 0.00160 plus 0.00160. So at equilibrium, we have no more hydroxide. It was a limiting reactant. We have 0.00160 of this, okay, and 0.00 on 0.00. I have the answer right here. 0.002150. 0.002150. Okay, now notice we've got, well, I'm not going to do that. All right, those are moles. Those are moles. And we now need to divide by our liters to get our concentration. It looks to me like we added 40 milliliters to 50 milliliters. So that is 90 milliliters, which is 0.090. 0.0900, which gives us a concentration of both products that are left to be, I just lost my place. Let's see, that's the base. So, okay, this one is 0.02389. This one is 0.01778. Okay, molar, and that's my acid. Molar, that's my base. I do have an extra sig fig, but that's good because I'm not finished. Now, that was just my stoichiometry step, okay? And notice I had to use my limiting reactant. If the other had been less, then it would have been my limiting reactant. Now I need my equilibrium step, okay? That right there was actually my stoichiometry step, right? That was the stoichiometry step. Then we divided to get the new concentration. Now I need my my equilibrium step, because look what's going on. I've got some of this and I've got some of this floating around in my solution, and they need to come to equilibrium with each other. So when they do that, we actually have two options. I'm going to give you the option you probably don't want first. Most students prefer the next option. But this option is to create a whole new ice chart. And this time I plug in 0.002389 and 0.01778 minus x plus x plus x, 0.02389 minus x, 0.0177 plus x, Ka equals 1.8. pKa equals 4.75. Okay. All right. I'll show you the easy way in a minute. pKa equals 4.75. Ka equals 10 to the negative 4.75. I did not do it this way here because this is not the way you want to do this, but I am not about to start over. So second log negative 4.75. I should have a negative exponent. Yep. So Ka equals 1.8 or 778 times 10 to the negative fifth. equals X. Hold on. Let me slow down. Let me slow down. I'm not being a good teacher, right? Ka is equal to H over the times the acetate over the acid. Ka equals X over 0.01778 or times over 0.02389. Okay, hold on, we know Ka. It's time to go ahead and plug that sucker in there. 1.8 times 10 to the negative fifth. Or we just said 1.778. We don't usually get that. Okay, do your math. Times 0.02389 equals divided by 0.01778 equals X equals 2.389 times 10 to the negative fifth. That's equal to H plus the pH equals the negative log of 2.389 times 10 to the negative fifth. Negative log, second answer equals 4.62. Okay, so what I want you to realize, I'll go over the easy way. Surely there'll be another example problem, right? Yeah. What I want you to realize is in part 1, this substance had a pH of 4.74. The buffer had a pH of 4.74. Oh, never mind. Okay. With a pH of 4.62. That's all. That's all. We didn't have a buffer solution. We didn't have a buffer solution. Let's look at the next problem. My apologies. We should be on this one, yeah, 4.62. So we should be here. I'm sorry. We have 2. You might not have 2. This is old. I've got methanoic acid. It really doesn't matter what the formula is. I've got a Ka of 1.60 times 10 to the negative fourth. I need to know my pH. I've got 23.90 milliliters of a 0.100 molar hydroxide. And I've got 25.0 milliliters of a 0.100 molar methanoic acid. I'm not exactly sure what that's going to look like. HCO, I don't know. So let's just call it HCA. Call it HA. Geez, that's usually what I do. That's what I have here, just HA. It's your generic weak acid. Okay. All right, so once again, what we see here is we are adding, we are adding OH to HA. All right. We need two steps. We've got the stoichiometry step where we need moles. All right. And we're going to do this easier this time. We're going to do the same type of problem, but a different way. You're going to like this way better. So let's get moles. 23.90 milliliters. Every 1,000 milliliters, 1 liter. Every 1 liter is 0.100 moles. Moles of what? Hydroxide. That is equal to 0.002390. Let's do the rest with our methanoic. 25.00 milliliters. Every 1,000 milliliters is 1 liter. Every 1 liter is 0.100 moles. When you multiply that, you get 0.002500. My hands hurt from writing so much, you guys. Okay. If I am adding OH to A, then they both need to be reactants. HA plus OH. That OH is going to take every bit of H it can. Strongest base there is. Let's plug in our moles, or let's start with HA, 0.00250, 0. And here we've got 0.002390. We're not worried about our water, and here we have 0. If we had some of A, we would put it there. And if we did, we'd have a buffer solution. And if we did, we would not see a very big change in our pH. But we do not have a buffer solution. So we're going to see, we're not going to have that. We don't know what the pH was originally, but we need to know what pH of it is now. So my hands hurt from writing. ICE. What's the limiting reactant? Once again, it is hydroxide. Minus 0.002390 minus 0.002390 plus 0.002390. And this will be 0.000110. Okay, now check this out, guys. Check this out. Oh, my hands hurt so bad, y'all. Let's divide this by the total volume. 23.9 plus 25.0. 23.90 plus 25.00. 48.9 milliliters, which is 0.0489 liters, which is our total volume. If something goes wrong here, I'm not stopping this video. Because I didn't do that here. Oh yeah, I did. Oh yeah, I did. It's going to be 1.22. Oh, good. 2 times 10 to the negative third molar HA. Okay. This is going to be 2.656 times 10 to the negative second. I think molar. Yeah. A. All right. Now, let me go backwards. We have the Stoich step, just like we did before, right? We have the Stoich step. Then before, we got our new molarities, just like we just did. And then we did a new ice chart. And we solved for X, and we got our pH. We did it the hard way. I think this problem was made to be done that way. Doesn't matter. But look here. The second step, which is the EQ step, can either have the ice chart as above, okay? Or you can use the Henderson-Hasselbalch equation. It will be brought up later, but maybe we'll be focusing on it in a different way. It is pH equals pKa plus log concentration of the conjugate base over the concentration of the acid. And it even works if you just plug in the moles, but I don't do that. pH equals pKa. Right, the last one gave us the pKa, so we should have used this equation. This time we have the Ka. And we have to use the Ka to get the pKa. So remember that pKa equals negative log of Ka. So pKa equals negative log of 1.8 times 10 to the negative fifth. I'm pretty sure that's 4.74. pKa equals 4.74. We'll make sure. Oh gosh, it hurts. It hurts. It hurts. Oh, this is methanoic. It's 1.6 times 10 to the negative fourth. I'm glad I just saw that. This is not ethanoic. So it's not 4.74. I've actually got that written right here. It's 1 point. Let's just go like this. Let's just do this, guys. Ka, as we wrote above, is equal to 1.60 times 10 to the negative fourth. Okay. So pH equals negative log 1.60 times 10 to the negative fourth. That is the pKa, plus the log of the concentration of my base. That is this here. Over the concentration of my acid, which is this here. All right. My pH, if I do that correctly, should be 5.13. Okay. 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 All right. Oh, man. Okay, guys. Oh, we have more problems to do, don't we? Dang, I don't know if my hands can handle it. Last one. That was the last one. Was that the last one? Yes. Okay. We didn't even experience buffer solutions. I don't even understand. I guess we'll have to do more. Okay. Okay. I'm a little confused. See you guys. It's kind of weird, wasn't it? The buffers, but those weren't really buffer examples. But it was. Okay. It'll work. We can easily work with that. Okay. Bye, guys.